DiPiazza. She's a senior scientist at the CNR, which is the National Council for Research in Italy. She's specifically at the Marine Engineering Institute. She's been she is actually the head of the Palermo section too. She's also an adjunct professor at the University of Palermo, and she's an expert on a number of things. But today she's going to talk about microgrids. Okay, which is I consider that another enabling technology for the energy transition. So,
thanks for the introduction. Well, good afternoon, everyone. First of all, I want to say that I'm really pleased to be here, to give my contribution to this summer school, and I want to express my thanks to organizers for having involved me. Well, my presentation is focused on microgrid paradigm, which is one of the most relevant solutions proposed in the field of electrical power system to enable an effective and durable energy transition. Okay, I will show you the impact of this paradigm on, with a special focus on a special application, which is the shipboard power system. I will show you some technical trends in the sector and showing the manifold advantage of the microgrid approach. And shortly, I will hint at some technical challenges which are still open. Okay. To understand the role of microgrid in energy transition, we should establish what is the meaning of energy transition. According to a classical definition, energy transition is a pathway toward the gradual decarbonization of the energy sector for reducing carbon dioxide emission and so to mitigate the issues of climate change. But really, even if climate neutrality and environmental sustainability are the leading constraints in this process, this is a more complex paradigm shift, which involves also societal and economic issues. For example, future trends predictions show an increase in energy demand in the future up to 28% by 2040. But at the same time, they need to improve the access to energy worldwide, and together with the need for improving, for example, resilience of our system, as well as reliability of the provided delivered electricity. All these issues call for the creation of a new energy ecosystem, whose main idea relies on the concept of decentralization. Well, microgrid is just a decentralized structure which can help to solve in the field of electrical power system all these energy transition related challenges. Okay, some definition. Microgrid can be defined as a small-scale, self-controlled power electrical system encompassing electrical generator, usually distributed, electrical load, storage system, and within defined electrical boundaries, which can be, for example, due the typical size range of going from 100 kilowatt up to several megawatt. For example, an university campus, so city district or a small village, and this is the size of a microgrid usually. The microgrid can interact with the upstream main power grid and can be operated both in grid-connected mode, so in coordination with the upstream power grid, or independently from the main power grid in isolated or islanded mode. In this structure, there is no more the need for high voltage transmission and distribution system, and this goes in the direction of increase of efficiency of electrical system. At the same time, we have the possibility to allocate many renewable sources, and this goes in the direction of reduction of the impact of energy production on the environment. This structure can also perform an intelligent management of loads and power sources, for example, by means of the interconnection interfaces, which are power electronic converters. And Giovanni Spagnuolo will talk to you about power electronics. Nanogrid can be considered as a building cell of a microgrid. It is a smaller in size, with the power not exceeding 50 kilowatt. It is a more affordable and a very customer-centric structure, and can be used in coordinated mode with other nanogrids, with the other microgrids, and with the main grid, and it can support other grid, for example, in a situation of emergencies. Okay. From a comparison between existing power grid and the new concept, the new smart microgrid concept, we can understand the level, the extent of the paradigm shift. The existing grids are very centralized structure, whereas small, few centralized high power plants deliver electricity power to many utilizers. In this structure, we have a very low use of ICT or distribution automation, for example, and both data and power flow are unidirectional from the producer to the customers, to the users, which are placed usually at very long distance from the point of production of energy. Okay, this system is intrinsically not very efficient because of the power losses that we have in the transportation and distribution of energy. At the same time, the system is not so resilient, for example, for anomalies in the system itself, or in presence of extreme environmental conditions, some failure in the system can propagate and can cause very large outages in the overall system, and real blackout in any case, for example, due to domino effect. On the contrary, smart microgrid is inherently decentralized. It relies upon multiple small scale, small size generators. We are distributed, we are local, so are close to the users. And smart microgrid is also allocate many renewable share, high rate of renewable generators, and is equipped with communication infrastructure which allow the components of the microgrid to communicate with each other. And for example, this allows final users to participate actively to the energy market as prosumers, and more in general, the bidirectional data flow that we have in the microgrid allows to modulate power flows according to chosen to fixed optimization objective, so to manage the grid according to our needs, for example, economic, for example, environmental, and so on. Okay. A crucial system in the microgrid is the energy storage system, whose role is the role of supporting the microgrid in several operating scenarios. For example, by smoothing out the intermittent renewable generators, or providing voltage support or frequency regulation to ensure the stability of the grid. And also it can contribute to increase the resilience of the system when this energy storage system is used as a backup supply system. Summarizing, the main components of the microgrids are a set of energy infrastructure and a set of ICT supporting generation, storage, use of energy, metering, monitoring, and advanced management of electricity, communication, and protection system, where protection is related not only to protection against fault, but also with reference to privacy protection services. By the point of view of control and management, microgrids are usually governed by multi-layer, multi-level control philosophy called hierarchical control, which is composed of three main layers for the achievement of the microgrid objective, which are, for example, voltage and current control and power sharing among the different generators at the lower level, synchronization with the upstream main grid or power quality control in the secondary level, and decision making or microgrid supervision, for example, for a resilient and profitable operation at the upper level, tertiary level. This control can be put in practice, can be realized by the simultaneous use of a local controller of the power authority interface, interconnecting, for example, generator, loads, or a storage system to the microgrid, and coordinating all these controllers among them. In this diagram, there is a summary of all the benefits that we can obtain by the point of view of energy transition by using microgrids. There are benefits by the point of view of quality of electrical power, by the point of view of impact on environment, by the point of view of energy access, and so on. And the coexistence of such benefits makes the use of microgrid particularly advantageous by the point of view of reliability, efficiency, and stable and green energy. For example, the possibility to have an intelligent management of loads and sources has an impact on both reliability and efficiency, as well as the possibility to supply ancillary services to support the upstream grid gives an impact by the point of view of reliability and stability, and the reduction of distribution power losses due to local generation, because generators are close to the user. Gives a contribution by the point of view of efficiency of the microgrid. Okay, in a nutshell, we can say that microgrid is a practical and accessible solution which obviously contribute to the decarbonization of the energy mix, but also improves the power electrical systems by several points of view of reliability, accessibility, energy cost optimization, flexibility, possibility for the final user to participate in demand response programs, and so on. Okay, let's pass to our application case. Okay, the application case is the shipboard power system, SPS for simplicity. In particular, we will speak about a shipboard power system in large passenger ship, because their size is similar to terrestrial microgrids, very, very large systems. Okay. This case study, this application case, is particularly interesting because the implementation of a microgrid on a vessel, on a ship, concern issues of energy transition by at least twofold point of view. By the point of view of electrical grids, obviously, but also by the point of view of sustainable mobility. Some background information are useful to frame this application case. We know that the contribution to pollutant emissions by maritime transportation is not negligible. For example, there is a recent study published by Transport and Environment about cruise ships that showed that a single fleet of cruise ships from a unique large shipping company emit in the atmosphere the same amount of sulfur oxide as all the motor vehicles circulated in Europe. And from this one can understand the need to totally revise, totally rethink the ship of power system usually currently used on board to cope with the environmental protection issues, but also to make the system compliant with the requirement of energy efficiency imposed by regulatory bodies, like, for example, the International Maritime Organization. In particular, because currently used systems do not optimize important aspects like fuel consumption, pollutant emissions, energy efficiency, and etc. Okay, the work in this field is particularly important by the point of view of societal and environmental challenges, but also by the point of view of industrial development, for example, with reference to the so-called blue economy and to the development of energy-related technologies. And this is reflected in very strong political and scientific engagement on this issue. For example, in the European Green Deal, in the establishment of the waterborne zero-emission transport partnership, and within the European Commission strategic programming. Okay, let's pass to the state of the art of SPS for the case study of a large passenger ship. This is the scheme of the currently used electrical power system on board. The system is called Integrated Electric Power System. The classification of SPS is made on the basis of use of onboard electrical power. This scheme, this state of the art has been established in the mid of 80s of the last century. In this configuration, we have only one group of electrical generator providing all the required power on board, delivering power necessary for both propulsion and for other services on board. This scheme has been preferred to previous segregated solution where two different groups provided separately power for propulsion and power for other services, because with this configuration we can reduce the number of generators and so reduce the capital cost and the maintenance cost. The main technical trends respect with the state of the art goes toward two main technical paradigms, which are the decentralized generation on board and the use of direct current for power distribution on board. This main technical trend has been supported also by sector roadmap, for example, the one proposed by the Electrical Ship Office of the US Navy. And we can notice that both the two philosophies proposed for power, power generation and distribution on board are supported by two important enabling technologies, which are the energy storage system and the power electronics that will be progressively more and more pervasive on board. All these trends converge toward the definition of a new SPS, which is a concept of microgrid on board. In this synoptic scheme, we can see the main involved technologies. I would like to put your interest on fuel cells, which are one example of low or zero emission power generation source, which is a promising solution for the implementation of decentralized generation on ships. Okay. We cannot, in this transition from EAPS to a microgrid, it is not appropriate to disregard all the achievement obtained in the terrestrial application, which is a more mature domain. And so it is very important to catch the opportunity to take advantage of all the results already obtained in the terrestrial application and to transfer this result to the maritime domain according to a terrestrial marine cross-fertilization approach. In particular, the good lesson can be learned by the domain of the smart buildings, where very efficient nanogrids have been realized, which with feature of the advanced management capabilities, micro renewables and micro energy storage integration, and where the use of DC distribution is a reality, especially for some application, like for example the data centers. Okay, within a collaborative project that our institute did with in cooperation with Fincantieri, we proposed a new approach for design and operation of a distributed generation on board, proposing the configuration shown in the figure, where we can see the integration of a diesel electric generation group supplying propulsion load, integrated with a set of several distributed low or zero emission generation systems supplying the hotel loads on the ship. The expected innovation of this configuration are obviously a reduction of polluting emission thanks to the use of low emission generation units, reduction of the size of the electrical system components, and the use of a simpler electrical grid thanks to the use of a lower number of conversion stages on board, safety of the ship using a criterion of redundancy in the design, and economy of scale by adopting a criterion of modularity. Okay. An important issue in implementing decentralized generation on board is the choosing of the most appropriate generation unit to allocate on the ship. One of the most promising technology is that of the fuel cell. In particular, according to a study on fuel cell on shipping by European Maritime Safety Agency in cooperation with the accredited certification body DNVGL, the best technologies are the ones shown in this slide. First of all, why fuel cell and not other kind of generation? The reason is that in a passenger ship, a fuel cell is very advantageous because of high efficiency, because of low emission, but above all, because of the absence of rotating or moving part. So these power sources supply energy without generating vibration or noise. Okay. As for these three technologies, we have the proton exchange membrane fuel cell, which is the most mature technology used also in the automotive field. This low-cost technology has a good efficiency, but has the disadvantage to be highly sensitive to impurities in the fuel and to work at low operating temperatures, so it is not efficient to use waste heat recovery in this kind of fuel cell. The high temperature PM cells, on the other side, has a lower sensitivity to fuel impurity, but has also a lower efficiency and a shorter operating life. The newer technology is the solid oxide fuel cell, which is very, very promising because of high thermal and electrical efficiency, but above all, thanks to the possibility to be fed directly by conventional fuel. Is a very important aspect, but on the other end is as the disadvantage to be larger in size and to have a high sensitivity to vibration and a limited operating life. Another issue linked to decentralized generation on board is the need to use an energy storage system together with the fuel cell in order to overcome some limitation of the fuel cell, for example, the low dynamic performance and long time to start up. The centralized generation unit is usually formed by a fuel cell used in conjunction, in association with the battery of another energy storage system. There is much research work in this period concentrating on the choice of the better structure, for example, in terms of the number of conversion stages to be used to set up this hybrid system. One of the results obtained in this literature reference is that the greater is the number of converters, the more are degrees of freedom in the management of the system. For example, we can avoid the unwanted interaction between the two systems, fuel cell and batteries, and above all, we can finally tune the control of the charge and discharge of batteries, so to, for example, prolong to increase the useful life of the battery. The other paradigm is the DC distribution on board. There are many scientific papers, technical standards, roadmaps, research program, also commercial solution proposed on such solution, because the advantages are really manifold. The most important advantages are the reduction of the footprint of the electrical plant equipment, which means a reduced volume and weight of the electrical equipment on board. The reduction of fuel consumption, because in a DC system we can operate the prime mover of the generation system at variable speed, so we can set this prime mover in its optimal point of operation and we can reduce the consumption of fuel. This is not possible in a AC system because we are constrained by the fixed frequency that in ships is usually 50 Hz or 60 Hz, and so the prime mover has to run at fixed velocity speed. Okay. There are other advantages by the point of view of power quality, and as a future potential, this system is well compatible with the onboard decentralized power generation, so the two paradigms are compatible between them. Okay, the proposed solution are the medium voltage DC, hybrid AC-DC solutions, and low voltage DC only for small size ships. The medium voltage DC has been proposed by the IEEE regulatory committees. This is a notional scheme of the proposed distribution system. It has eliminated many of the limitations of AC systems and want to respond to the need, to the increased power need on board, but currently has not been yet realized on board due to the lack of industrial components and to the lack of protection system at medium voltage DC. This is a well-known and consolidated solution. This is a turnkey commercial solution proposed by ABB in the last decade. The name is onboard DC grid platform. It is suitable for any marine application and installed power lower than 20 megawatt and operates with a DC with a 1 kilovolt DC system. In this slide, we can see the quantification of both fuel consumption reduction and weight reduction of electrical plant with reference to the case study of a platform supply vessel. We have some % of reduction in fuel consumption and 26% reduction in the weight of equipment. These slides refer to a real-world case study we have analyzed within the project with Fincantieri, considering the cruise ship whose features are listed in the table. We have focalized our attention to the subsection of the plant downstream, medium to low voltage transformer substation, which is called secondary distribution, and we have transformed by AC to DC is part of the electrical grid, obtaining the possibility to remove several power transformers which have been replaced by power electronic converters, obtaining a very significant reduction of weight and volume. Weight variation has been in the order of 35% and volume variation of the order of 31%. This reduction in weight and volume is very important because reducing the weight of an empty ship as a consequence, a reduction of fuel consumption, obviously. This is the second case study. We did a similar work, but in this case, we realized that a totally new electrical microgrid where the distributed generation has been applied by using a fuel cell and battery system, and obtained results are given in this table: a reduction in weight of 17% and 24% for the volume. And this is a very interesting result because the weight and volume reduction obtained by elimination of transformers and replacing AC with DC is more relevant than the additional weight and volume due to the electrical equipment we have to add for implementing this decentralized generation. We have 22 additional pieces of electrical equipment, in particular fuel cells, batteries, and respective power electronics interface. Okay, I'm going to conclude with some technological challenges and regulatory barriers for the implementation of all these proposed solutions. As far as the DC-based electrical distribution is concerned, especially for medium voltage DC, The obstacle is the absence of commercial off-the-shelf equipment, because currently equipment for naval application are still conceived and built to accept fixed AC frequency in input, and the absence of suppliers able to produce, to give validated and de-risked medium voltage DC component discourages both designers and the investor to put attention in this solution. By the point of view of fuel cell on board, the problems are related to production, supply and storage of hydrogen, also for reason of safety, and there are also deficiency in regulation. For example, if you want consider solution where the hydrogen is directly stored on board, we have to do some specific risk assessment studies to evaluate the situation. There is no regulation on this. Other main open issues on the implementation of DC microgrid on board are stability issues and protection issues. As for stabilities, SPS are always weak grids with low inertia and limited generation capability, so power imbalance can easily lead the system to instability situations. The solution is the need for suitably controlled energy storage system and careful consideration of voltage stability, starting from small signal and large signal analysis, because especially in presence of some kinds of load, which are the so-called constant power loads and pulsed load on board, even if pulsed loads are usually present in military applications. As for the protection system, you see in DC system that fault current can reach up to more than 100 times the value of the nominal current in very short time. So the consolidated protection system for AC system are not appropriate, and the protection system has to be totally revised. Starting from the fault protection strategies to grounding, and also for protection devices. For this last aspect, some simulation we did show that an electromechanical circuit breaker, for example, is totally not suitable to clear a fault current in a DC system on time to avoid the total outage of the system. And as protection devices, solid state circuit breaker are the candidate solution because of the very short velocity of intervention time. Okay, small intervention time in the order of tens of microseconds. Also, wide-band semiconductor devices are to be considered due to their low losses, high voltage operation, high temperature operation, and possibility to be operated at high switching frequency. Okay, concluding remarks. We have seen that microgrid and nanogrid plays an important role in the energy transition process, and they are important both in terrestrial application and in SPS. Currently, there is an ongoing process of reassessment of all the naval electrical system to increase the efficiency and sustainability of ships, and the prevalent trend is the transition from a currently used integrated power system to microgrids on board. There are several key enabling technologies, such as DC distribution on board and decentralized generation, which are the most important paradigms to be translated on board, and this will be possible thanks to the enabled technologies of storage systems and power electronics. And finally, there are some open challenges on which researchers are still to work, in particular on the aspects of stability and protection. That's all.
Thank you very much. Oh, super quick, Maxime.
Okay.
Thank you, Professor, for presentation. I have one clarification and one question. The clarification is, if I understood right, the microgrids and nanogrids are basically the same thing, but the different scale, right?
Nanogrid and microgrid?
Yes.
Yes, it's a different scale.
Yeah, but basically the principles are the same.
Yes, yes.
Okay, and the question is, how does this technology fuel cell work? Because I'm not engineer. I don't know, maybe some few aspects of it, because I have no idea at all.
And what is the question about fuel cell? What do you want to know?
How does it work? What is it?
Okay.
Yes.
As a conversion system, is electrochemical, so your colleague can give an explanation better than I, because I'm an electric engineer, that converts hydrogen into electricity and give as output only water, so is a clean, very clean power sources as considered renewable, low or zero emission energy sources. I speak of low emission because on ships it is not possible to have pure hydrogen. So there are some systems that convert fuels into hydrogen, and these give as a result some pollutant emissions. It is not so. It's not always a zero emission source.
Thank you.
We had Riccardo first.
Very quick consideration and then a very quick question. The consideration is that, if I understand correctly, there is a switch from a centralized energy system to a decentralized system, so like cells, but they're not isolated, they speak one each other. So maybe this is a parallel with humanities, with the concept of global local. So from a globalization to a global local, so local system, but not isolated, but talking among each other.
Yes, I like this comparison, yes.
Yes, maybe there is a further synergy potential. And then the question is the most important regulatory challenge you see the one on hydrogen storage for this type of systems? You think that the most important regulatory, so legal issue is the hydrogen storage point on protection and safety. So if you think of one legal area to improve, I
think that legal can improve all the shipping sector, because there is much work for a lawyer in this field. Obviously, there are some regulations to be established because, for example, hydrogen on board is several problems with safety because it's explosive, and the safety on board is really important constraint, is a requirement of pivotal importance on board. There is a regulation from International Maritime Organization, the SOLAS Convention, is the Convention on Protection of Human Life at Sea, which imposes many constraints to make human being very, very safe on vessels. For example, there is a paradigm which is the safe return to port, which has been introduced after the sinking of Costa Concordia, which imposes a revision of propulsion system on ships in order to ensure a backup solution also when everything is not working. Safe return to port.
Yes, maybe it's a stupid question, but I'm also not an engineer, and I was wondering, like first your introduction was microgrids, and I understand the concept, I think. And then the other point is exchanging the fuel system or the system with which you can run ships, kind of. And as far as I understood, it's just changing these very polluting fuels with hydrogen. And why is it then the point to have a microgrid on a boat? Like having a hydrogen system, does it imply having a microgrid system?
I'm not sure if I understand your question. Okay. When I proposed the centralized generation, the fuel cells, which are based on the use of hydrogen as fuel, are not used to as a propulsion system, not to move the ship, only to supply services, hotel, room, and theater, and this kind of services on board. This is the first part of your question. Okay. Can you repeat the second?
No, I think then the fuel to drive the boat is still the same.
Diesel.
No. Diesel is yes. There are there are other proposed fuels like, for example, LNG. Okay, because gives low emissions, low.
Because I thought like the boat is always microgrid, kind of, because the boat is not connected to any grid, so I don't know.
Isolated, yes, these are in isolated, because microgrid is connected to the main grid, but also isolated. Okay. For this reason, microgrid gives a greater resilience to the electrical system, because if I get a problem on the main grid, I can operate in isolated mode, and so I can assure the continuity of supplying energy to people in the market.
I'll allow one very last question from Sutrika.
Basically, I understand that microgrid can be intelligently used to different power sources and then.
Yes.
So I have curiosity from the ships, why can't we use photovoltaics along with fuel cells? And
Yes. There are.
Naval TV.
It is possible to use photovoltaics on ships. There are Carnival ships. Carnival is a shipping company of cruise ships, which have used the photovoltaic plant to supply the shopping center on the ship, on the cruise ship. Cruise ships are very, very big system. Okay, it's a smart city on the sea. Yes.
Okay, well, we have to move on, unfortunately, but hold your questions. Carmela, she's still around. So let's thank you once again. And now, another one of these very important enabling technologies for the electrification transition. And so we have Professor Giovanni Spagnuolo. He's a professor at the University of Salerno, but he is also one of the most influential minds and IEEE fellow for his many contributions in the field, especially of control, power electronics, photovoltaics, among many other things. So very excited to hear about.
Thanks a lot, Rami. Yes, thanks a lot, and thanks for the invitation also to Alessandra. We go at a lower level with respect to the previous one, because I will speak to you about switching converters and power electronics. You will discover that you are using also now some thousands of power electronic converters in your equipments, in computers, in your smartphones, and you don't know, maybe. No? So we will see that power electronics, also Maria Carmela and also Francesco spoke about the fact that power electronics is an enabling technology, meaning that it guarantees the connection between the systems that you have, for instance, into a smart city, and the loads. So they are a sort of interfaces. No? At the first glance, we can say that they are interfaces for letting you connect loads and generators. This is the first level of comprehension of this kind of devices. Switching converters allow to implement smart grids, but not only, because I wish to introduce the idea of a switching converter of power electronics by some examples that you are also in your pocket as me in this moment. So basic working principles, it is quite difficult. You will see that it is quite difficult to explain in 40 minutes how a switching converter works, but for sure, I can show you a very basic example that is close to all the applications that my colleague spoke about before, and I'm confident you will understand even if you are not an electrical engineer. What are the products available on the market? I will show you very few examples of products that allow you to implement cases like examples like smart grids, for instance, that are on the market, especially for the PV part, the photovoltaic part, as it is much more close to my competencies. And also I will show you what are the major challenges for the future applications of this technology. I took as a first slide this first page of a very famous and a milestone of power electronics book. If you are interested in, of course, this is the reference. And because there is the definition of power electronics. The field of power electronics is concerned with the processing of electrical power using electronic devices. So very simple. But here there is a description of some power electronics converter, but it is quite important this last sentence. Control is invariably required. So you can understand from this page that this is not only a processor of power, but there is a mix also of control. This means microprocessors. No? So it is a mix of signal electronics and power electronics. When you analyze the power electronic converter, the switching converter, you have to face both problems and both level of currents and voltages. This is an example of where power electronics is in this moment. Keep into account that, for instance, my grandfather did not use any power electronic converter in his life, maybe, but we use a lot. And this is a first demonstration because in an electrical car there are a lot of converters. For instance, these are in this picture there are recorded some of them because you need some converters for going from the battery charger, so when you recharge your car, up to the high voltage battery, which is the battery that allows the car moving. So you see, this is an interface. No? This is an interface between the grid and the battery. So first interface. Another interface, another switching converter from the high voltage battery to the ancillary load. So for instance, the radio and so on. So another interface, which is a switching converter. But also here you see bidirectional converter, so a converter that processes energy from one side, for instance, DC. DC means direct current, so current and voltage levels are constant over time, or AC, because AC means alternate current. This means that the variables are sinusoidal, both voltages and currents. So you see that also here there are also other interfaces towards the electrical motor, because also the electrical motor needs to be controlled properly in order to accelerate, decelerate, braking, and so on. So converters are more or less interfaces, but you will see that they are not only limited to interfaces. Another example is this one, which is a logical scheme of the electronics, the power electronics that is in a smartphone. You see that there is a core of the system, which is power management system. Power management system is a processor, more or less, so signal, low power system, that is interfaced with a lot of systems that allow to the power management system to operate over the video, over the audio, over the antennas, over the vibration system, ELID, and so on. So you see that in a smartphone there are a lot of systems powered by power electronics. And this is the main board of an Apple iPhone. I don't remember the version, but it doesn't matter. And you see that in this slide, all the power electronics devices and integrated circuits are highlighted. I have highlighted some of them. But for instance, there is, let me check. This small one is wireless power receiver. So when you switch off the wireless system on your smartphone, you are activating a switching converter. You don't know, but it is so. And so on. You see that they are a lot on the main board. And also when you recharge your iPhone with a wireless charger, you are using a switching converter. You know that, or maybe you don't know exactly because you know this part of this slide, but what happens in this application is that the magnetic field that is emitted by the plate that you are on the table is linked, but you don't see it because it is a magnetic field, is linked with the receiver that is in your smartphone. And the magnetic field, the coupling between these two circuits allows you to recharge the battery in your smartphone. And you see that there is this coupling. These are the two coils that are one in the base, one in the smartphone, that are magnetically coupled. But for, let me say, feeding and controlling these two, you need a switching converter because you have to feed them in a proper way in order to couple them properly and to have the maximum transfer of energy from the source, that is this one, to the load, which is the receiver, let me say, of the energy, which is this one. So also in this case, you see that there are a lot of these are schemes taken from the scientific literature and from some documents that are made available from the producer. You see that there are switching converters, like this one, strange symbols, but it is a switching converter, battery charger, and so on. So at the end, you have to drive these two very old systems, because keep into account that these two systems are very old in electrical engineering. They were invented maybe 200 years ago, no? But to drive them in order to have this function has been a system invented 50 years ago, maybe. Okay, so very recent. Indeed, history is very recent of this technology, because you see that this is prehistory, but it is quite close to my date of birth, no? 1957, but I'm not very old really. No? But at the end, during this life, you see that at the beginning, and this was the reason why I said that my grandfather did not use any power electronic circuit, but because there were any compact component, for instance, to be put into the smartphone. No? So this was the reason why smartphones were not invented at the time. And moreover, you had that during the story, we arrived up to 1980 when the actual components were invented. And you can see, of course, you cannot appreciate the size of these systems, but this is a system for very high voltages and currents. These two components are for lower voltages and currents. And you see that in this slide, I've put into evidence the fact that power electronics is not only big current and voltages, but also low power electronics. And indeed, you see that in this arrow, I have put into evidence that the power components that are this one are coupled with the invention of microprocessor or the use on a large scale of microprocessors, because the two things are linked. And in this case, there is the link between IGBT, which is was and is very innovative power component, with the DSP, which was invented by Texas Instruments and used for a lot of industrial applications. And now replaced by more advanced processors, so more compact and able to do more and more operations per second, so more fast systems. And this is another interesting plot in which that I found it very interesting. In order to show you during the years, and you see the years here, how many calculations per second per $1,000 are able to do these processors. Because as I'm saying, power means also to have a very powerful processor. And you see that we have reached a significant value in this moment with the Core i7 plot, and we are going towards the processing capacity of the human brain. Maybe we will arrive in some moment to this. So this means that also the power electronics can perform more operation or more evolutive, let me say, operation through the electrical power. This is a scheme that you have already seen in the previous presentations, and you see that this is the smart grid, so generation, distribution, commercial and industrial loads, residential loads. When you look at these pictures, that seems to be quite logical, but indeed they are, but they are at a very high level of comprehension. You have to keep in mind that at the lower and lower and lower level, there are a lot of power converters. Because, for instance, when you wish to interface the generation with the distribution, you need power converters for doing what? For sure, for doing, in principle, some operation that is done also in your smartphone. No? But in this case, operations that especially are dedicated to the change of, let me say, the shape of your power. No? Because previously I mentioned DC and AC. So in many cases, as also Maria Carmela said, no? We have the need of changing the level of voltage and currents, even if we remain in DC. So, for instance, we have, I will show you some example. We have 48 volts, but we need, for some application, 12 volts. So we have to shift the levels of voltage and current, but it is always in DC. In some other cases, we need to change AC, so sinusoids, going up and down at 50 Hertz, in sinusoids that go up and down at, I don't know, 10 Hertz. So this means that sinusoids input, sinusoids output, but different frequency. No? Or to change the shape of the power, let me say, no? Because we need from AC to DC or vice versa. And we will see some examples how to implement this change. In this case of smart grids, in many cases we have this need, and we have in every point of connection we have a switching converter doing this. Of course, the power level is much more high than in the smartphone, but the idea, the principle is the same. The principle is, of course, also implemented into a different way because we have different levels of current and voltages. Indeed, this is a summary of the four topologies I'm speaking about before. And you see that I will start from this component. We have a lot in the smartphone because in many cases we need what to do in the smartphone. Typically, we have a battery working, I don't know, at 12 volts, let's suppose, but maybe the screen of your smartphone works at 3 volts. No? This is just an example. So you need to move from 12 volts of the battery to 3 volts of the screen. So you have to change the level, and you need a switching converter. Or you need to go to another level because the vibracon works at a different level. So you need another switching converter from the battery, which is at 12 volts, at the voltage at which the vibracon works. The same holds also in the car, not only in the electrical one, but also in the one that mostly we use every day. So the one with the thermal engine, because for instance, the battery that you have in a classical car is at 12 volts. But for instance, the lights work at a different level. So also there, although it is not an electrical car, you need a level shift that is done efficiently through a DC to DC converter. And you see that this can be appreciated much more by electrical or electronic engineers or students. The power entering here is usually the product of the voltage by the current. And it is, at least ideally, equal to the power that exits from the converter. So we reason, at least at the first level comprehension, with converters that have an efficiency equal to 1 or 100%. Of course, this is not possible because nothing is for free, no? In engineering and in the life. So we have that the power at the output is not exactly equal to the power at the input, but a lot of research is ongoing in order to take this number not at 70, 80, 90%, but as much closer as possible to 99 or even more percent. This is the DC to DC conversion, so level shifting. These two are quite related because I will show you that at least in principle they can be implemented through the same circuit, at least in principle. And you see that you change constant variables, constant input. So you see I've used the capital letter as it is used in electrotechnics. You change in current and voltages that change in time. T is time. So they are usually sinusoidal. The same also here, because the variables are over time, so functions of time here, but constant. No, this is AC-AC. AC-DC, constant at the output. Instead, in the AC-AC, the cyclotron converter, usually known in this way, there is that both are variable. These are the four topologies, no more. It seems to be simple. These topologies are, in many cases, put together, it is said in cascade, in order to achieve some functions. For instance, this is a scheme, quite complicated, but you will see it is quite simple to understand. It is a scheme that you have, for sure, for instance, when you recharge the battery of your smartphone, because this is the AC line, so 220 that we use every day, sinusoidal. Then there is a first converter. Here it is named the transformer, but more or less it is an AC to AC converter or AC to DC. And you see that here it is still a sinusoid, not equal to this one, but let me say a smaller sinusoid. Then there is the rectifier. This is another name of the AC to DC converter. And indeed, you see here that the waveform is different. And I put this slide here just in order to let you understand that one thing is the ideal behavior of these converters. 100% efficiency, input and output perfectly sinusoidal or constant. But another thing is the reality. This is indeed here, it is not exactly by using the real circuit, it is not a DC perfect, mathematically speaking DC, but it is something like a DC. And indeed, we need a filter in order to smooth this variation of the waveform. And indeed here, we have smoothed it. Not constant perfectly, but it is more close to a constant voltage and current. Then there is a regulator. I will show you an example of a regulator, which is a DC to DC that supply the load that in this case, in the example I'm doing, is the battery of your smartphone, to supply the battery with the current and voltage that allow to recharge it as faster as possible because you want this. Okay? This is the first example, quite complicated slide, but it is easy to understand. This is a power electronics converter. It is a DC to DC because I have bought a battery, the battery that we use in a car, and you see that it is 12 volts. Okay, but I have a fan because it is hot, not here in Trentino, but in my city for sure. And here we need 24 volts, for instance. No? So how to couple these two things? Because I have a battery at 12 volts and a fan at 24 volts. How to couple them? By means of a switching converter. No? In this case, the switching converter is driven by a microprocessor, which is hidden inside the box that you buy at the shop. And you see that what I have put into evidence, but I don't want to lose time in this moment. Maybe if you are interested, you will look at these formulas. It is quite intuitive that if this is an ideal converter and the input power has to be equal to the output power, if you have 12 volts here and a given current, of course, if you want 24 volts, because of the fact that the power is the product of voltage by current, you need to have an output current that is the half of the input current, because you increase the voltage and you have to decrease the current. It is quite intuitive. Of course, this is not mathematically, let me say, exact in practice, because there are some non-idealities, but more or less it is so. And in this DC to DC converter, how we drive this DC to DC converter? Because you see that here there is a link. I've named it data, because the processor generates signals of some microbuds, so low power, but this is a big device managing more power for supplying my fan. From where in this system the control logic comes of course from the fan, because for instance it is too cold for me, so I wish to reduce the speed of the fan, so I have, for instance, to reduce the voltage I supply to the fan. For instance, I have to put 12 volts as I have in input. I can do this by means of the switching converter by doing what? By commanding something that say to the processor, please reduce the voltage at the fan because it is too cold for me. So I can regulate the voltage here, so the speed of the fan, by simply programming, for instance, programming the processor or commanding the processor through the classical command that you have on any fan. This is what happens inside the system. But if I wish to have a control from a human, feeling if it is too cold or too hot, of course you need the regulator. No? But instead, if you know that in your room you wish to have an increase of the speed of the fan, then to keep it constant, and then to reduce because the external temperature is reducing, you can program this processor in order to do this every day. And what programming the processor means, of course, to write some lines into some software and program this processor, which can be programmed even by the producer of the system. No? So at the end, everything is done by the matching between power electronics, which process the power coming from the battery, interfaced with the processor, which is the brain of the system. What happens if we use the same system, but by controlling photovoltaic panels? Because in this case, we have that the input is photovoltaic panel, so the power production from the photovoltaics can change during the day because of irradiance, non-irradiance, temperature high or temperature low. And so the input power now is changing, but the output is now, let me say, constant, is a sink of power because it's a battery, and I wish to recharge the battery. I've put this example in this talk because this was one of the key points when I interacted some years ago with, maybe you know him, Giovanni Soldini, who is a very famous sailor going all around the world by his ship through only wind, because he asked me, okay, I bought some PV panels for my boat in order to recharge the battery, because of course they have the battery on board in order to keep on the lights, emergency signaling and so on. And he said to me, okay, I bought these panels, I connected these panels to the battery, but they don't work. So photovoltaics is useless. And I explained them, I explained it. At that time, switching converters in photovoltaics were used only by very, very expert people. I said, okay, you are wrong, because for 10 years, you have not bought the switching converter for interfacing both. Try to put the switching converter in the middle, and you will see that photovoltaics is powerful. And indeed, I, together with a colleague, I designed the switching converter for him. He mounted on the system, and he was so happy that when he came back, he founded a new company for producing PV panels. So, and the key point was the use of this system, because this system, in this case, note the difference with respect to the previous slide. I wish to keep the previous slide for you. The information, in this case, comes from the output of the converter, because you were the intention to regulate the speed of this flow. Instead, now, the information comes from the input, because the constant part is the output. And you wish to track the operation of the PV system in order to let it produce the maximum power, because you wish to exploit the system as much as possible. Indeed, so keep in mind that the input now comes from this side. Why? Because you see here that photovoltaic systems have some, you see, power versus voltage curves that are like this. So they have a maximum. So there is a specific voltage at which they have to work, at which they produce the maximum power, as you may see. So I have to be so smart, a word that they use a lot. I have to be so smart in order to track the position of this maximum in the power versus voltage curve of the PV panel, so that it produces the maximum power. And this was the point that Giovanni Soldini, of course, is a smart person, really, but he was not aware of this. So at the end, in this, and you see that the maximum power point, so the peak of this curve, change with the irradiance, but also with the temperature. For instance, in my city in the southern Italy, maybe we have the same irradiance as here, but there are 20 degrees more, maybe. So the power production of the same panel is not the same. And I need a controller that is so smart to track this maximum power point if it is installed with the same PV panel and the same battery here in Trentino Alto Adige or in my city in Campania. And in order to do this, of course, there are some strategies that are implemented where? Always here. Because the producer of this device, which is a battery charger, a solar battery charger, does exactly this with the implementation of this system before selling it. Programming that system in order to control in the best way the DC to DC converter, which is a battery charger. And just for showing you a practical example, so the error, the mistake that Giovanni Soldini did, you see that maybe he, this is only an example, it is not exactly the example of Giovanni, but maybe he interfaced the classical battery at 12 volts here with a panel like this. And you see that if the panel works at this voltage, so without the switching converter, but plugging them as they are, you see that the power produced at different irradiance level is never the maximum. Because there is not a perfect matching between the source, the PV panel, and the load, which is in this case the battery. So this was a possible error. And you see, okay, this PV doesn't work properly because the power production of this PV is much less than what I expected. because the producer, when you buy the PV panel, say at 1000 watt of square meters irradiance, you can produce 370 watts. But Giovanni said, no, the recharging of the battery was ineffective, because really in that case, the production was not 370, but maybe 100 or something like this. But there is even a worse error or mistake. Suppose that you wish to recharge a 48 volts battery by means of the same PV panel. What is, you plug and you say, okay, it works. But it doesn't work, because you are matching the same panel with a battery at 48 volts. And you see that the voltage is wrong, because it is out of the voltage range in which this panel can work. And what is the power production you obtain by this matching? Zero. You obtain 0 watts. So you have spent a lot of money for not recharging the battery. And maybe this was the error or the mistake Giovanni did. For instance, this is an example of PV battery charging. This is the company that Giovanni built up together with a friend of him. And you see that this PV panel is also, you can search on the web. This PV panel is also flexible, because they invented a polymer in which to, for doing this sandwich, to protect the cells, in order to have some adaptation of these panels to the curvature of the boat, or even of other surfaces. And you see that this red square is the protection of the switching converter, of the DC to DC converter, which is embedded. So he has understood the importance of this device, which is embedded into the PV panel, so that you can buy this PV panel and plug now directly to on your battery by so you are sure that the battery will be recharged. And indeed, these are the specifications. Sorry, they are in Italian, but you see that the indication is that this can be matched to 12 and 24 volts battery safely by recharging it for sure. Some other devices are available on the market, and they can be adapted to any PV panel and to any battery, because of course everybody now has understood that it is not possible to connect in order to have the best performance, the battery and the PV panel without any switching converter. Here you see that there are many differences. This is for lithium batteries. This is for lead acid batteries with different voltages. So you have only to choose on the market which battery.
How much does it cost? Just an idea.
The objective was to have that the cost is lower than the PV panel, because if you say, okay, I don't have to buy the PV panel only, of course people said, I don't want PV. But if the cost of the panel is, I don't know, 150 euros, the cost of this is 7 euros, 10 euros. This is an example of switching converters, other switching converters on the market. A lot of numbers, but this is only an example of the fact that they are, this is one of the many are on the market. This is not for your smartphone. This is for a little bit larger systems, but you see that there are a lot of, you can see, input voltage range. So it is not, they are also flexible. So they work in a range of input voltage, and they ensure to you 1 and 2 outputs. So they are very evolved in a so small system, because you see that these are the dimensions are in millimeters. So 2 centimeters. So small, 2 centimeters. I don't remember, yes, the thickness. But in any case, the electrical functions are to have one output, and you see a lot of different outputs. The output 2 can be also negative. In some application, the voltage needed is negative. And you see, I put also this example in order to let you see the efficiency achieved. No? So this is an important point, because I said you that theoretically the efficiency is 100%, but nothing is perfect. No? So at the end, you have to pay the 20% more or less of power that you put at the input of the device in order to have this function. So if you put 1 watt at the input, you will have 0.8 more or less watts at the output. You have to pay something. But I can say you that in some other cases, this is a general purpose device, but you can even find 97, 94, 95. It depends on the voltage level, current level, integration, level of integration, and so on. Indeed, this is another type of converter, much bigger, and you see in the previous case, the power was 5 more or less multiplied by 3 are 15 watts. This is a device managing 15 watts more or less. Instead, in this case, 20 kilowatts. So 3 or 4 order of magnitude more. So a giant thing. And you see that in this case, the engineering has been much more sophisticated. So the efficiency is even more high. This for let you see that there are different applications, different size. You see that this is also cooled by air, because the hot produced inside the converter is significant. What is the meaning of this sentence? If the system becomes hotter and hotter because of the behavior, this means that the efficiency of that system is not 100%, because the input power is not equal to the output power, and the difference, because the output is lower, and the difference is transformed into hot, because the system becomes hotter and hotter. And you have to remove this hot, because otherwise you risk that the circuit does not work properly. So you need also fans for removing this heat from there. And of course, this has an effect on the efficiency. But all inclusive, these guys have reached peak efficiency of 98%. I have a few minutes, but this is quite intuitive. How the inverters work? We have to transform the DC power from the battery into power in AC for switching on the lamp. So in AC means that we need sinusoids, positive and negative, in terms of voltage and current. But how this system works? You see that I put 4 switches. They are more or less the switches that we use for switching the light on and off, but of course more sophisticated. But in principle, you can think they are the same switches. And you see that during a first phase, only 2 switches are closed and the other 2 are open. So that the current from the battery flows in this direction. So remember, from left to right into the lamp and come back. But just after some time, for instance, we can say, what happens that the 2 switches that were closed before are now open and the other 2 are closed. So that the current flows in the opposite side, from right to left. This means that during the first phase, current on one side, from one side to the other phase in the other side. So you have realized more or less a square wave, positive, negative. So this is not a sinusoid. Yes, this is true. It is an approximation of the sinusoid that you have realized by means of this thing. And if you need to emulate the 50 Hertz sinusoid from the grid, you have to switch on and off these couples of switches every 25 milliseconds, which is equivalent to 50 Hertz. So they switch, of course, if you try to do this by the switch every 25 milliseconds, you become crazy quite soon.
With 4 fingers.
Yes, exactly. But This is done, you can understand, by means of some semiconducting device, so some electronic switches that are, of course, commanded by a microprocessor, again. So at the end, the switches are switched by a microprocessor, and they are transistors, so semiconductor devices. So this is the square wave, but there are some other way of switching these switches in a more fast way. Of course, you need a more advanced technology, and you can understand why my grandfather was not able to use this kind of technology because it was not invented. And you can find in some places also on the devices you can buy, on the inverter you can buy this acronym, which is pulse width modulation, which is a technology that is used in order to have not a sinusoid, but a thing that seems quite far to be a sinusoid, but I can reassure you that it is more close. But for understanding this in detail, you need to study the Fourier theory, which is quite advanced. But trust me, it is so. But for doing this, we need again some very powerful processor that has been invented maybe 15 years ago or 20 years ago, not at the beginning of the past century when my grandfather was living. Finally, for switching faster and faster, we need new components. And indeed, you see, I remember that also Maria Carmela showed something like this. You see that in order to switch faster and faster, you need to switch lower power, so that the more fast you switch, the less power you are able to switch, to process. So if you want to process 1 megawatt at 1 megahertz, this is impossible. But in our smartphone, we have to switch low power, because the smartphone processes low power, so we can switch quite fast. And this allows the producer to produce very, very small switches. So this is the reason why your smartphone can stay in your pocket, because the switch is very fast, and thus the components are very small, because the power that has to be processed into the smartphone is really small, with respect to the power that you have to switch into a train, for instance. No? In that case, you need very big components. Quickly, some examples. These are inverters for PV applications, and you see that the inverters now on the market allow you to connect PV panels, wind energy system, because if you have the space, you can put also a small wind mill at your house, the battery, and supply all the loads in your house. So smart devices. And finally, the conclusions. So you can understand, I hope, more than before, that power electronics is crucial in every power management system, from low power to very high power. Different constraints in consumer or industrial applications because of the fact of the switching frequency that I mentioned to you before. A large number of solutions are on the market because many producers from China, from Europe, from wherever you want, with different also reliabilities, as you may imagine. But further work is needed for improve the efficiency, because we need to increase the efficiency of these devices because we use too many of them. So to improve the efficiency of these devices by 1% means to save a lot of energy. Integrate digital technologies and power electronics, so digital energy. I remember also Maria Carmela cited this. Improve reliability and extended lifetime, because we need to avoid to change power electronics frequently. For instance, for a PV system, for a PV plant, you risk to change 3 or 4 times the inverter during the 25 years of lifetime of the plants, and this is not acceptable at all. No? And use of artificial intelligence for learning habits, because in a system where for instance, in a house in which I use the fan, no? the system has to learn what are my habits, what is the best speed, depending on the fact that depending on the fact that I am in front of the fan or my wife, which suffer much more the hot or much less the hot. No? And digital techniques for energy exchange with the grid, because this is crucial in order to, as Francesco said, to exchange in one way or in the other way the energy on the grid. Before ending,
Marketing.
this is marketing, but before the coffee I can do it. With the colleagues, in particular with the colleagues from Trieste, we have launched the first energy-related national PhD at an Italian level. Our two universities are together with the other 20 universities in Italy. This PhD, this national PhD, is a new experiment that was allowed by the Italian ministry. And our idea is to have the network of universities covering from cells, so technologies for the cells, up to the grid connection for the formation of new professional figures for the energy transition and also for the PM part. So we have also 12 co-funding industries, and I wish to invite you to visit in Preview, because it is not very stable up to the moment, because the call will be open on June 24, which is San Giovanni also, so it is in my honor, but the call will be open for 2 or 3 weeks. So if you are interested into applying for these scholarships, of course, you are welcome. That's it. Thank you.
Thank you very much, Ivan. And we have very, very clear presentation. Questions? Okay.
One clarification.
You mean if the process is managed by computers?
Processor.
Yes, processor is the processor that you have in the computer, so the chip.
And it's not the converter.
No. When you buy the converter on the market, they say, okay, this is the DC to DC converter. But inside, you have to know that there is not only the unit that processes power. There is also a microprocessor which guarantees you the control of the converter, but on some models also not for consumer usually. It gives also the possibility, for instance, to plug a USB connector for downloading data. And this is a quite interesting property, for instance, of photovoltaic inverters, because when you buy the photovoltaic inverters, which is a switching converter, but inside there is a processor. Of course, if you plug by a cable, according to the specifications of the producer, you can download some data about the efficiency, about the production. There is very often a wireless connection with your smartphone for checking this, and which is the component that guarantees this processor, which control the system, acquires the data, and provide you all the data you want. And also transmits this data to the producer of the inverter, maybe because they are interested in collecting data.
So the difference between the inverter and converter is that, like inside of the inverter, we also have the microprocessor.
Between the inverter and
the converter.
No, it is the same. Converter is more general.
Okay, more general. Yeah.
Converter is more general.
But but the inverter is the converter to PV that has like also the microprocessor.
No, the inverter is maybe I was too fast on this slide.
DC plus.
Exactly.
You
have to check. You have to check this slide. Okay, because see, inverter is this function, rectifier is this function.
Okay.
Everyone is a converter.
Yes, converter is more general. But you have to keep in mind that into this box, there is also the processor. So there is everything.
More questions?
May I ask just, in your view, how the miniaturization in the industrial production is an enabling factor to increase this kind of technology?
For reply to this question, I can say you that there are some groups in Netherlands especially and in Belgium that are working on the fact that they wish to integrate the DC to DC converter I showed for the PV application into the panel. So they wish, you know that, maybe you know that the PV panel is made of 2 layers, plastic, let me say layers, in which there are the cells. And they are in some way glued one in another so that it is a sandwich. No? So it is one system, very resilient with respect to humidity and so on. And they are trying to integrate into this very thick, very thin system the converter. So the integration, of course, is quite important because
So the manufacturing is an issue.
yes, definitely, and because to integrate the switching converter into a smartphone where power is quite small is a quite simple issue. But to do this with when you have into a PV panel 10 amperes, quite difficult. Yes.
Small question. You showed us the example of the conversion from DC, from the battery, back to the bulb, from DC to AC. And the vice versa from AC to DC works by the same principle.
Exactly.
By the switchers.
Yes, I was too fast on this, but because I saw the time was expiring. But you see that here you have source, so able to generate power, and load, because the lamp, it is well known that is not able to generate power, not absorbs all.
At least,
But at least up to now. But instead, the battery can be even recharged. So, for instance, into a motor of a car, of a bike, no? When you go on an electrical bike, you can even put some power through your body in order to recharge the battery. Why? Because here there is your body, and when your body needs not to push, you absorb power from the battery. But when you are able to push the cycle, you have a flux of energy on this way. So this, but again, if you have only the switches, this function is not able to be implemented. Who is able, the thing that is able to implement this is the microprocessor that control the switches in a proper way.
The smart.
Sorry?
The smart detail.
Exactly.
Processor.
Exactly. Power is nothing without control. This is more or less.
also in your life.
Yes.
Okay, I think we need to move on, but Giovanni is around for any more questions. Sure, for questions at the bar, maybe. So let's thank you once again. We're slightly behind, and we have a busy day today, so let's reconvene here at 5:20. Okay. The later you get in, the later we finish.